So far in thermochemistry, we have looked at specific heat for the different phases of water and for different samples to use the equation Q equals mc delta T to calculate the energy. But what about the spots on the heating curve where there is no temperature change? If there's no temperature change, then Q equals mc delta T is going to give us delta T of 0, no temperature change, which would give us 0 energy. However, lab data shows that there is energy even though there's no temperature change when an actual substance goes through a phase change. So that would be like melting or boiling. So we have a different equation that we use, and instead of using specific heat, we use a different constant called latent heat, which has to do with the potential energy between the particles as they change from one state to another. So our new equation is Q equals HM, and this is an equation used to solve our thermo calculations during a phase change. So we've got our Q, that's heat transfer, and again, if Q is positive, then it's endothermic. If it's negative, it's exothermic. Then we have H, which is the latent heat, and we have M, the mass, in grams. So latent heat is defined as the heat required or released when changing phase. And like we said before, when a substance changes state, there's no change in temperature. So this aligns with these flat sections of our heating curve. And you can see that these are labeled. So if you notice the unit, it's joules per gram are the units. So temperature change does not have any impact on this. It's just how much is going to be going through the phase change, and that is going to be our latent heat. So we have two values that we're going to use. Fusion and vaporization are fancy ways of saying melting and boiling. So the heat, H of fusion, which you might see written as H little FUS, so that's heat of fusion. This is the process of melting if you're adding heat, or freezing by removing heat. And the amount of energy per gram at 0 degrees for water, since that's our melting point, it is 334 joules per gram. That's our heat of fusion, and that's written on the heating curve right here. And then our heat of vaporization, H vape, again for water, is 2,260 joules per gram. And it makes sense that it takes a little more energy to change things into a vapor because the particles have to spread out so much more to become a gas. And again, this is at the melting point, which would be 0 degrees for water, at the boiling point, which would be 100 degrees for water. Let's do a couple of examples. And so now we are not using Q equals MCAT, we are using Q equals HM, and we know that because we are going to be going through a phase change. Words like melt, condense, boil, those tell us that phase change is happening. So that is where we would realize that we're using heat of fusion or heat of vaporization, not Q equals MCAT. So let's do a few examples, and then you will be all set to work on the practice. How much heat is required to melt 25 grams of ice? So heat is Q, but we don't know. But we know we're melting, so that goes along with our heat of fusion, which is this constant 334, and we know our mass. So we've got Q equals 334 joules times 25 grams. And easy as that, our heat required to melt it at the melting point is 8,350 joules. Calculate the energy decrease that occurs when, here's our mass, 15.3 grams of steam condenses from vapor to liquid. So we know we're condensing, so we're using Q equals HM. And if we're going from steam to, I guess it's vapor to liquid water, then we are going to be using 2260, but we're actually doing negative because it's cooling. So this is just telling us it's heat released, really. And again, the energy decrease that occurs, that's all of those are telling us that it's going to be an exothermic process. So we've got our energy decrease and our mass. And multiply those and we get 34,578 joules. And that's the energy decrease. So we've got released. So both ways, both of these are saying the same thing. If you have a negative, that's released. Or you can just write the value and write released. Sometimes the negative confuses students. So I will just write released. And our last example, it says, is 1500 joules enough to fully boil 350 grams of water? So in this one, we're going to do the same problem, but we want to know if Q is 1,500 joules is sufficient. It's going to be larger than Q, equal to or larger than Q when we calculate it for 350 grams of water. So we are trying to boil. So that means we're going to use 2,260. We've got 350 grams of water. So if we multiply these two together, we get a really large number actually, 791 kilojoules versus 1.5 kilojoules. Is that enough? Nope, it's not. We need significantly more energy in order to boil it. So let's do another problem just to figure out, okay, how much of the water can we actually boil with this 1500 joules. So in that case, we're going to still use Q equals HM, but now we're going to plug in Q and H and say, okay, how much water can I boil with that much? It doesn't look like it's going to be a very significant amount. Yeah, as expected, a fraction of a gram. So that's all that would be able to boil at 1,500 joules absorbed. Only 0.66 grams can boil with 1,500 joules. The problem didn't ask us this information, but it's good exercise for us to practice solving for different variables than just Q. Okay, so there's our three examples using our heat of fusion and heat of vaporization. And again, you know that you're going to use this one instead of Q equals MCAT because none of these will tell you a temperature change, and they involve a phase change. Melting, condensing, boiling. All of the other problems that we've done up till this point have only been about a single state of matter, and that matter heating up or cooling down. So you are going to do this practice page for, again, the latent heat. Up here we've got heat of fusion and heat of vaporization provided for you, just in case you need those referenced. And then you're going to solve each of these, and the directions say match your answers to the letters in the box and then write the corresponding letter in its problem numbers blanks to reveal the secret word. So you have some secret letters down here. If your answer for number 1 was 1900 joules, you'd write E in the blank for number 1. I don't think that's the correct answer for number 1, but just for the sake of explanation, whatever your answer is, match it and write it in this blank, and then you'll have a word that's spelled out from 1 to 9. One word with all those letters at the bottom. And it'll be a quick way for you to check if your answers are correct also. Just following that same process of finding the energy using latent heat. Some of them you're finding mass, some of them you're finding the energy. So whichever one, solve for the variable you do not know.